Hello! In this video, we will check Cramer's rule and the inverse matrix and see how they work. Let's start with Cramer's rule. We start with one of the properties of determinants. The determinant of the product of two matrices is the same as the determinant of each matrix multiplied. This means we can find the determinant of AB either by doing the product first, then calculate the determinant, or by calculating the determinant of A and B and multiply the determinants. Keep this result in mind since it's the main reason why Cramer's rule works. When we get a system of equations and we need to solve it, there are multiple ways of doing it. The usual way to solve for the input vector uses elimination. However, Cramer's rule solves it by using determinants. Knowing the property we mentioned earlier, how can we use it to solve for the input vector? To be able to use the determinant property, we need to have an n by n square matrix. But the input and output vectors are n by 1. We need to extend the input and output vectors and turn them into matrices. If we take a look at the identity matrix, it's the matrix that doesn't produce change when multiplied by another matrix. The usefulness of the identity matrix comes from the fact that its determinant is equal to 1. If we exchange a column of the identity matrix with the input vector and we look at the determinant calculation, we see if we exchange a column from the identity matrix with the input vector, we get a component of the input vector as the determinant. Which component we get is based on which column we replaced. Now, if we multiply the matrix A by our new input matrix, we get an output matrix that has the output vector in its first column, because we multiply the input vector column by the matrix A. The second column of the output matrix will be the second column of A since we multiplied the matrix A by the second identity column. Taking the determinants and apply the determinant property gives us the first component. To get the second component, we simply exchange the column positions in the input and output matrix and calculate the determinant and so on. So, is this an effective way to solve a system of equations? Let's look at the cost. The amount of determinants we needed in our example was 3, which were the determinant of A, the determinant where the output vector is in the first column, and the final determinant where the output vector was in the second column of the output matrix. For an n by n system, we need to find n plus 1 determinants. Each determinant is the sum of n factorial terms, so we multiply n plus 1, which is the amount of determinants, by the amount of terms for each, and we get n plus 1 factorial terms. Don't forget that to find each term you also need to multiply. The calculations are way too much for this method to be effective. And now, let's check the inverse matrix, an idea we are familiar with, the idea of the inverse. Can we have an inverse matrix, a matrix that carries out the operations needed to transform the output vector into the input vector? We know that the inverse of a function takes the output and gives us the input. The idea of an inverse matrix is similar. For a given output vector, we multiply it by the inverse of a matrix to give us the input vector. First, let's see the definition of the inverse matrix. A matrix A is invertible if there exists a matrix such that if we multiply the original matrix by it, we get the identity matrix. Whatever A does to the input, A inverse reverses these operations. It means that the inverse matrix cancels out the effect of the original matrix, giving us the identity matrix, compared to composing a function with its inverse function. Another cool fact about inverse matrices is the inverse of the product. If we have two invertible matrices A and B, the inverse of the product is B inverse times A inverse. This reversal of order might look new, but we actually did the same thing when we inverted functions. For example, let's take the square root of x squared minus 1. What we do when we invert this function is take the last operation, invert it, then put it as the first operation. The second operation is the subtraction. We invert it, then put it as the second. Then we take the first operation of the original function, invert it, and put it as the last. As we saw in the example, the reversing of the order also occurs in reversing functions. In functions, we reverse the order of operations. In matrices, when we invert the product, we reverse the order of the multiplication. A nice way to remember this fact is to think of it as wearing your shoes. You start with the socks, then the shoes. Then taking off your shoes is the inverse, in which you take off the shoes, then the socks. So how do we find the inverse matrix? Let's take a look at the systematic way of solving for the input vector. We take a system of two equations as an example. We multiply the first row by a constant and add the two equations to isolate the second variable in the second equation. Then we add the second equation to the first to isolate the first variable. The last move is to divide by the constant multiplied by any variable. If you pay attention to what system we ended up with after these operations, it's the identity matrix. The operations we just did took the system from the matrix A into the identity matrix. If we express this operation in matrix form, we will be able to get the inverse matrix. What we have to do now is to express elimination and isolating variables in terms of matrix multiplication. The type of matrices that does these operations are called elimination matrices. For example, if we want to multiply the first equation by -3 and add both equations, we put -3 in the bottom left corner of an identity matrix. Now we need to isolate the first variable, so we add the two equations. In this case, the second equation is multiplied by 1, which we add to the top right of an identity matrix. Now we have isolated the first and second variable. Division is required when the isolated variables are multiplied by a constant. Division could simply be done on a matrix by dividing the entire row by a constant. Now we have two matrices that represent elimination and isolation. After we multiply these two matrices, we divide each row by the constant next to the variable. The matrix we end up getting is the inverse matrix. It transforms A into the identity matrix, which is the definition of the inverse matrix. This is exactly the action of Gauss-Jordan elimination method to find the inverse matrix. We augment the matrix by putting the matrix A and the identity matrix next to each other. As we do the elimination on A, we do the same on the identity matrix. This is the same as multiplying by an elimination matrix. The identity matrix keeps a record of the elimination steps and division occurs as the last step. If you enjoyed the video, consider liking and subscribing, and see you in the next one.